Hello, today's video lesson is going to be a more advanced techniques on Lewis structures. I'm going to cover exceptions to the Lewis structure rules. Okay, and also talk about resonance structures, and hopefully if there's time I'll get into what's called formal charges. Okay, alright, so to start off with, let's look at what's called resonance. Okay, we were looking at the structure for O3. Okay, and if we drew the Lewis structure for O3, what we got, or we ended up with, was a Lewis structure that looks something like this. Okay, where we had electrons arranged in this fashion here. Okay, if you don't remember this, go back and watch this video, but you should all be able to get this Lewis structure at this point. Again, make sure your dots look really nice, everything looks nice and neat. Make sure these dots aren't all stuck together. There's a nice separation between these two, and these two. Anyway, the point here is that what we're looking at, in order for here's the problem with this, by the way. Here's the issue. If we look at this structure, okay, what this is telling us is that there's a single bond here and that there's a double bond here. Now, single bonds by themselves are longer than double bonds, and they have less energy than a double bond. So if we're looking at this Lewis structure, we should see a distance between these two. If I call that distance 1, and this one I call distance 2, well, I should see a difference in those distances. When we look at the data for ozone, distance 1 equals distance 2. Okay, that's a problem because that's not what our Lewis structure is showing us. The other problem is that the bond energies for both of these are about the same, but our Lewis structure is not indicating that. So there's a limitation to Lewis's simple model because Lewis didn't realize, because his model came before quantum mechanics, that electrons aren't localized. This is called the localized model. What that means is that electrons are in between these two nuclei of the oxygen atom, and these 4 electrons are between these. But remember, Heisenberg's uncertainty principle says we don't really know where the electrons are. We know that they're most likely in this atom and most likely in that region called the internuclear axis between the two nuclei, but we can't say for sure where they are. So there's a problem. The electrons are zipping around throughout this whole thing, that these electrons are not just here, but they're also over here at the same time. Yeah, I know, it's kind of crazy. So we need to draw a Lewis structure that is going to show that. Okay, so what we have to do is we have to draw the same Lewis structure that we have here. Okay, draw it again, and what we're going to do is we're going to replicate the bonds on both sides. So I'm going to have that single bond here. I'm going to draw this, and this is what's called resonance. Now, I'll talk about how you know resonance is going to happen in just a second. But to fix this model, what I do is I draw brackets around this, and I draw a double arrow pointing in both directions. Draw another bracket, and I just duplicate the same structure, but I change the bonding. Oops, I probably should change the bonding, right? So I'm going to change the electrons on both sides. So now I'm going to have a double bond over here and a single bond on this side. Now, I'm not flipping the molecule over. Don't misinterpret this. I did not take this molecule and just flip it over and get it over on this side. I kept the oxygens in the same spot as they were, so they didn't move. What I moved were the electrons. It's the electronic arrangement that is changing. The electrons on either side are different, and they're going to be replicated on both sides. That is what's different, okay? Okay, so there is your correct structure for ozone. So ozone would have to be represented like this as a resonance structure. So how do you recognize when something has resonance? Well, what you're looking for is a central atom that has atoms on either side of it or all around it that are the same. That doesn't have to be the same as the center atom. It's just that they have to be the same atoms on the outside, meaning 2 oxygens on the outside. Okay, and therefore the bonding also has to be different, and that's the second criteria. So let's take a look at another example. If I take a look at CO3 minus, okay? If I look at the carbonate ion and I draw the Lewis structure for the carbonate ion, I'm going to end up, and I'm not going to go through the rules and the steps on the Lewis structures, I'm just going to draw them out here because I know what they look like. So I'm going to draw 1, 2, 3 for the oxygen. I know this is what it's going to come out to when I follow my rules for Lewis structures. Okay? So what I'm looking for is that I have an atom that has a central atom surrounded by elements that are the same. So 3 oxygens surrounding that central atom. And the bonding is different. So really what you're looking for first is whether you have all the same bonding or if you have differences in the bondings. Well, in this case, since I have differences in the bondings and the atoms are the same, Now I'm going to have resonance. Now let's say, for instance, that this were hydrogen here. If this were a hydrogen, there wouldn't be any resonance in here. It's only between the two oxygens. So the resonance only occurs between the elements that are the same with different bonds. All right, so charge of -2, by the way, not -1. Okay, so charge of -2. Now, one other thing that I have to do is if I'm doing ions, I need to put that -2 out here. So if I have an ion, no matter whether it's resonant or not, I still put brackets and I put a -2. Okay, so the brackets have dual use. Now, for this one here, I'm going to have to draw 3 of these structures. I have to draw 3 of them. I'm going to put the double bond here. And again, take your time. I know that you can kind of get sloppy with these. So make sure that you go back and fix any dots that look like lines or you're unsure. I'm telling you, you don't want to lose points on a simple Lewis structure because you were sloppy with the dots. And I see that quite a bit. Brackets around this. Brackets here. Do the same thing for the third one. Another set of brackets. And we're going to do 3. I know these can get a little boring, a little tedious, but you know that is chemistry, by the way. So nothing you can do about it. And I kind of find these a little, therapeutic. So they kind of keep me sane. Anyway, I'm going to stop rambling here. 2 minus, 2 minus. Okay, and there is your resonance structures for carbonate. Okay, O3. All right, a couple other exceptions I want to talk about is. You probably remember these from Honors Chem. Okay, Boron Trifluoride. Now, if I follow the rules for Boron Trifluoride, it looks like I should get a structure that has fluorine, fluorine, and fluorine, and I should get a double bond here. Okay, now if you follow the rules, as you notice there, look at there, a little electron there. It looks like. Let's get rid of that thing. We don't want any sort of confusion later. So, okay, so. This is what you would get if you follow the rules. You're going to have to remember that boron is a deficient in octet. It will not be able to do this. Okay, if we think about the periodic table and where fluorine is on the periodic table in relation to boron. Okay, hold on a second. I'm going to get a periodic. All right, so now I got my periodic table. So if I look at fluorine here, fluorine is on the right side of the table. It has a higher electronegativity than boron. Boron's way over on the other side. So our electronegativity of fluorine is going to be way higher, so therefore boron, which is going to attempt to try to create a double bond with fluorine, is not going to be able to do it. Why? Because its electronegativity value is just way too low. That double bond is never going to happen. One little thing about fluorine is it will bond one time, and that's it. Okay, so don't forget to draw your electrons in here. So you have electrons here, 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 here. I'm going to stop drawing all the electrons in just to save some time in the videos, okay? But you should always draw your electrons in. Now, fluorine will always bond one time, one bond, never double bonds, ever. Okay, you're never going to draw a structure where you're going to see fluorine double bonded to anything. So your structure for boron trifluoride would be this, except you're going to put the electrons all around. Okay, so boron and beryllium are going to follow this rule. Okay, just boron and beryllium. Why those two? Again, because in order to get that double bond to happen, boron's going to have to try to pull electrons from these more electronegative elements, and it cannot do it. Now, if it gets further down to the bigger ones, yeah, because the ionization, or the effect, say that again, the electronegativity gets weaker, it's definitely going to be able to pull those electrons at some point, but you're never going to see that. Anytime you see boron, and even beryllium is even weaker than boron, it's going to have a deficient octet. So remember, boron and beryllium, deficient octets. All right? Okay. The other exception to the Lewis structure rules is that we take a look at something like sulfur hexafluoride. All right, I'm not going to go through the steps, but if you try to do the steps and you try to do the calculations, you're going to be able, it's going to say something like 4 bonds. Well, think about it. If I have sulfur and 6 fluorines around here, okay, I'm going to need to have 4 bonds for these 6. So here's where the rules kind of fall apart. So what you're going to have to do is just go back and kind of go to the original rules where you just kind of join everything together and put your electrons on here. More times than not for these types of structures, you're never going to have, rarely will you have double bonds. I guess they do come up, but, if they do, you know what to do to handle. But go ahead and put your electrons in here. I'm not going to do it for all of them, but why is this happening is my question, right? This is what I really want to focus on, is why is this occurring? Well, if we take a look at sulfur, in its position on the periodic table, well, it's right here. It's in the third energy level. Right? This is the first energy level, second energy level, third energy level on the periodic table. Now, what sulfur has going on for it is that because it's the third energy level, it has a d orbital open to it. So not only can it bond and have an octet, but it can actually go beyond the octet, because even though it doesn't use the d orbital in its ground state formation, when it actually bonds and puts atoms together with it, it can then utilize that d orbital. Okay, so this expanded octet, okay, this octet that goes beyond the 8. Now, 8 is not for everything, right? We see it's not for everything. So when we get to expanded octets, we can definitely go beyond, only if it's in the third energy level or beyond. So it has to be third energy level. Why? Because the d orbital is available. So you got to make sure that you mention the d orbital. That's really the crucial part. And why would it be? Because that's where the third energy level starts at. So you can see there are a lot of elements that can actually go beyond the octet rule. I mean, there are. We don't tend to see them too often, but there definitely are a lot of elements that can do that. Okay? So those are your two exceptions, okay, to the octet rule. And by the way, with boron trifluoride, it's an extremely reactive substance, extremely reactive because of that deficient octet. And it will react anytime it sees a set of lone pairs of electrons. So it will react with ammonia because it's got that lone pair of electrons on it. We're going to actually see this later on in acids and bases. Okay, so you can see that's, notice that I didn't like that bond there, so make sure it looks like a nice long bond. Anyway, so it sees these electrons, or it's attracted to these electrons. There's going to be a violent reaction between boron trifluoride and ammonia. And even in the water, because water has that lone pairs of electrons on it as well, so you're going to get a violent reaction. So you want to keep this away from any sort of moisture. Anyway, that's a little bit more than you need, but so watch for the deficient octets, watch for the expanded octets, third energy level d orbitals, beryllium and boron for the deficient, and don't forget about resonance. Okay? Alright, the last video I'm going to do on Lewis structures is on formal charges. I don't want to throw it in here because I'm going to keep it separate, but I'll do one last video on what's called formal charges, and we'll talk about those in class. Alright, thanks a lot, guys.